Welcome to the deep dive. Today we're digging into something absolutely fundamental. Energy.
It really is everywhere.
Right, from the food we eat, powering our thoughts, to the fuel driving cars and industry. Energy's constantly changing form.
And understanding those changes,
Yeah.
well, that's crucial. For chemistry, for the environment, for pretty much everything.
So this deep dive is all about thermochemistry. We're exploring energy, how it flows, especially as heat when chemicals react.
Think of it as listening to the universe's energetic pulse. It helps make sense of how chemistry links to big, real-world issues.
Our goal here is simple. Give you a solid, clear grasp of energy in chemical systems. We'll cover the core ideas, why they matter, and you won't need any charts or diagrams.
Exactly. It's your shortcut to understanding the energy that drives chemical change.
And it really matters, doesn't it? Thermochemistry connects directly to, well, how we power our world.
Absolutely. Fossil fuels, renewable energy, climate change. These principles are at the heart of those discussions. It's not just theory, it's about making informed choices.
Okay, let's dive in. Energy and chemistry, where do we start? What's the first big concept?
It starts simple. Energy is basically the capacity to do work or to produce heat.
Make things happen.
That's it. And the most fundamental rule, the law of conservation of energy. You might know it as the first law of thermodynamics.
Yeah. Energy can't be created or destroyed.
Precisely. It just changes form. It converts from one type to another. But the total amount of energy in the universe, constant, always.
Like a cosmic accountant keeping perfect books, so it changes form. We usually talk about two main types, right? Potential and kinetic.
We do. Potential energy is stored energy.
Okay.
It's energy something has because of its position, or maybe its chemical composition.
Like water behind a dam.
Perfect example.
Yeah.
Huge potential energy just waiting. In chemistry, it's about the forces between atoms, the energy stored in chemical bonds.
And then there's kinetic energy.
The energy of motion.
Yeah.
That water flowing through the dam. Now it's got kinetic energy. It depends on mass and how fast something's moving.
So back to that analogy people use, a ball on a hill.
Right. At the top, it's all potential energy. Let it roll.
It converts to kinetic, it moves.
But not perfectly.
Yeah.
Some of that energy always gets lost, well, not lost, but converted into heat because of friction as it rolls. That shows energy often transfers as heat.
Okay, that's a key point. Which brings us to something that trips people up. The difference between heat and temperature. They're related, but they're not the same thing.
Not at all. Temperature is about the average kinetic energy of the particles, how fast they're randomly moving or vibrating. It's a measure of intensity.
Like how vigorously things are jiggling around.
Exactly. Heat, though. Heat is the transfer of energy. It flows between objects specifically because they have different temperatures.
And it always flows from hot to cold.
Always.
Okay.
Until they reach the same temperature, what we call thermal equilibrium. The energy spreads out, basically.
Makes sense. So energy transfers as heat. What about the other way? Work?
Work is the other major way energy moves around. It's defined as force acting over a distance.
Like a gas expanding and pushing a piston.
That's a classic chemical example. The expanding gas is doing work on the surroundings. So heat and work are the two ways energy crosses the boundary between a system and its surroundings.
Okay, system and surroundings. But before that, you mentioned something about the path. State functions. Why is that concept so critical?
Ah, yes. State functions. This is a really important idea. A state function is any property of a system that only depends on its current state.
Not how it got there.
Exactly. Think about climbing a mountain, your final elevation change. That's a state function. It only depends on your starting and ending points.
Right. Doesn't matter if I took the winding path or scrambled straight up, the elevation difference is the same.
But the distance you traveled, that absolutely depends on the path. That's not a state function.
Okay. So how does this apply in chemistry?
Energy itself is a state function. The total energy change in a process depends only on the initial and final states.
But the amounts of heat and work involved.
Those can depend on the path taken. This simplifies things enormously, as we'll see, especially with calculations.
Got it. So to track these energy changes, we define our focus, the system and the surroundings.
Right. The system is just the part we're interested in, maybe the reactants and products in a beaker. The surroundings is literally everything else, the beaker, the air, the universe.
And this distinction helps us classify reactions based on heat flow, right? Exothermic and endothermic.
Precisely. An exothermic reaction releases energy from the system to the surroundings, usually as heat. Feels hot.
Like burning wood in a fireplace.
Perfect. The products end up with lower potential energy than the reactants. They've formed stronger, more stable bonds, releasing the excess energy.
And endothermic,
That's the opposite. Energy flows into the system from the surroundings, feels cold.
like an instant cold pack.
Exactly, or just melting ice. You need to put heat in to make it happen. The products have higher potential energy. Energy was absorbed to break or weaken bonds.
Okay, so we can talk about energy flowing in or out. But how do chemists actually measure this heat? That sounds like calorimetry.
That's the science of it, yes. Calorimetry. And the tool is a calorimeter.
And different materials react differently to heat, don't they?
They do. That's measured by heat capacity. It's the amount of energy needed to raise the temperature of something by 1 degree Celsius or 1 Kelvin.
And there's specific heat capacity.
Right. Specific heat capacity is the heat capacity per gram of substance. Water has a famously high specific heat.
Which is why it takes ages to boil a kettle, but also why coastal areas have moderate climates.
Exactly. Water absorbs a lot of heat without its temperature shooting up.
Right.
Great thermal buffer. That high specific heat is also why sweating cools you down so effectively. Evaporation takes a lot of heat away.
Clever. So what kinds of calorimeters do we use?
Well, for many reactions in solution, especially at atmospheric pressure, we can use something quite simple, like a coffee cup calorimeter. Basically, nested styrofoam cups.
Seriously, styrofoam cups.
Yep. Good insulators, and crucially, they keep the pressure constant open to the atmosphere.
And why is constant pressure important?
Because at constant pressure, the heat measured, we call it QP, is equal to the change in another important state function called enthalpy, symbolized as H. So HA equals QP.
Enthalpy. Okay, so in a coffee cup, we're directly measuring the enthalpy change.
Pretty much. We often talk about the heat of reaction and enthalpy change interchangeably for constant pressure processes. If heat is released, it's exothermic, H is negative. If heat is absorbed, endothermic, H is positive.
Okay, so that covers reactions in solution. What about things like burning fuel? That seems messier.
Definitely need something more robust. For combustion reactions or anything involving gases where pressure might change drastically, we use a bomb calorimeter.
Sounds intense.
It is. It's a strong, sealed steel container, the bomb. You put your sample inside with excess oxygen, seal it, and ignite it.
So the volume is constant.
Exactly. It's constant volume. Since the volume can't change, no PV work. W in each EV can be done. So W0T.
Ah, and the first law says A equal Q plus W if W is 0.
Then AE equals QV. The heat measured at constant volume directly gives you the change in internal energy, AE, not enthalpy.
Okay, subtle but important difference. AE at constant pressure, EE at constant volume.
Right. And this bomb calorimetry data is vital for comparing fuels. We find hydrogen packs about 141 kilojoules per gram. Methane, the main part of natural gas, is around 55 kilojoules per gram.
Wow, hydrogen has way more energy per gram.
It does, which is why it's so interesting as a potential clean fuel, though storage is a challenge.
That's a great practical link, but chemistry shows up in unexpected places too. You mentioned hot plants.
Oh, it's fascinating. Some plants, like the voodoo lily or skunk cabbage, are thermogenic. They can generate their own heat.
Like actual heat, how much?
Sometimes 10, even 15 degrees Celsius above the surrounding air temperature.
Why would a plant do that?
Good question. Often to attract pollinators. The heat helps vaporize scent compounds, spreading them further. Or, like the skunk cabbage, it can melt snow around it to emerge earlier in the spring. It's biological thermochemistry in action.
That's amazing. Nature's own little furnaces. Okay, so we can measure heat directly with calorimeters. But what if a reaction is, say, incredibly slow? Or maybe dangerously explosive? We can't always stick it in a calorimeter.
True. And that's where Hess's law becomes incredibly powerful.
Because enthalpy is a state function.
Exactly. Hess's law states that if you can express a reaction as the sum of several other steps, the total enthalpy change for the overall reaction is simply the sum of the enthalpy changes for the individual steps.
The path doesn't matter.
The path doesn't matter.
Yeah.
So if we want the enthalpy for reaction AC, but it's hard to measure, maybe we know the NH for AB and for BAC, we can just add those together.
And we can manipulate the known reactions too, right?
Absolutely. Two key rules. First, if you reverse a reaction, you just change the sign of its AH. Ectothermic becomes endothermic and vice versa.
Makes sense.
Second, if you multiply the coefficients in a balanced equation by some factor, say you double everything, you also multiply the AH by that same factor.
So you can flip reactions, scale them up or down, and then combine them algebraically to figure out the H for reaction you couldn't measure directly. It's like solving a puzzle.
It really is. We can calculate the enthalpy change for converting graphite to diamond, for instance, using their combustion reactions, even though you can't just burn graphite and expect a diamond easily.
Okay, Hess's law is handy, but finding the right combination of reactions sounds like it could still be tricky. Is there a more systematic way?
There is, thankfully. It involves using standard enthalpies of formation, usually written as OH degrees. The little circle means standard conditions.
Standard conditions. What are those exactly?
Good question. For thermochemistry, standard state means for a gas, it's 1 atmosphere pressure. For a pure liquid or solid, it's just the pure liquid or solid. For something in solution, it's a 1 molar concentration. And crucially, for an element, it's the form the element exists in at 1 attolam and usually 25 degrees C.
Like O2 gas for oxygen or solid iron?
Precisely. And here's the key convention. The standard enthalpy of formation of any element in its standard state is defined as 0.
That's our baseline, our reference point.
Exactly. So the H degrees of a compound is the enthalpy change when 1 mole of that compound is formed from its elements in their standard states.
Okay, so we have tables of these H degrees values for lots of compounds. How do we use them?
We use Hess's law again, but in a structured way. Imagine breaking down all the reactants into their constituent elements in their standard states, which requires energy, the reverse of their formation. Then imagine forming all the products from those elements, which releases or absorbs energy equal to their H degrees values.
So reactants to elements, then elements to products.
Right, because enthalpy is a state function. The overall H for the reaction is the sum of the enthalpy changes for those two hypothetical steps. It boils down to a simple formula. H degrees reaction equals H degrees their products. H degrees reactants.
Sum of the formation enthalpies of products minus the sum for the reactants, remembering to multiply by the coefficients from the balanced equation.
You got it. This is incredibly useful. We can calculate the heat released by burning methane, or the massive energy output of the thermite reaction, aluminum plus iron oxide, just by looking up values in a table.
That explains how we can compare fuels like methanol and gasoline, even if their combustion is complex.
Exactly. We can calculate the energy released per gram or per mole very precisely using H degree values. It turns out methanol has less energy per gram than gasoline components like octane, but it burns more smoothly, which is why it was used in some racing applications.
Fascinating trade-offs. So these calculations are vital for understanding our energy sources. Let's talk about those sources, primarily fossil fuels.
Right. Petroleum, natural gas, coal, they all formed from ancient biological matter over millions of years, essentially concentrated, stored solar energy from the past.
Petroleum, crude oil is a mix.
A complex mix of hydrocarbons. We separate it by boiling points in refineries into fractions. Gasoline, kerosene, diesel fuel, lubricating oils, asphalt.
And natural gases mostly.
Mostly methane, CH4. We get a lot of it now from shale deposits using hydraulic fracturing, or fracking.
Fracking is controversial, though.
It is. It allows access to vast reserves, significantly boosting U.S. energy production. But there are definite environmental concerns about water use, potential groundwater contamination, and induced seismic activity that need careful management and ongoing study.
And coal.
Coal formed from ancient plant matter. There are different grades, lignite to anthracite, with increasing carbon content and energy yield. It's abundant, but mining has environmental impacts, and burning it releases sulfur dioxide, a cause of acid rain, and significantly carbon dioxide.
Which brings us squarely to the greenhouse effect.
Yes, it's a natural process, actually essential for life. The Earth absorbs sunlight, warms up, and radiates energy back out as infrared radiation, or heat.
But some atmospheric gases trap that heat.
Exactly. Gases like water vapor, H2O, and carbon dioxide, CO2, are good at absorbing that outgoing infrared radiation. They then re-radiate some of it back towards the Earth's surface, keeping the planet warmer than it would be otherwise, like the glass in a greenhouse.
A natural, necessary effect. But the problem is a balance.
Precisely. While water vapor levels are relatively stable, human activities, mainly burning all those fossil fuels we just discussed, have dramatically increased the concentration of CO2 in the atmosphere.
We can see that in historical data, right? A sharp upward curve.
A very clear trend. More CO2 means more infrared radiation gets trapped, leading to an overall warming effect on the planet's climate system.
And we are seeing temperature changes.
We are. The patterns are complex, different changes in different regions, But the overall global average temperature is rising, and the last decade was the warmest on record. Climate modeling is incredibly complex with uncertainties, but the link between increased anthropogenic CO2 and warming is very well-established science, rooted partly in the principles of energy transfer we've been talking about.
Wow. So thermochemistry really does connect the microscopic world of molecules to huge global scale issues. Let's quickly recap the journey we took.
We started with the basics: energy, potential versus kinetic, and the fundamental law of conservation of energy.
Then distinguished heat from temperature, talked about work, and the crucial idea of state functions, like energy and enthalpy.
We defined system and surroundings, exothermic versus endothermic reactions, and looked at how we measure heat changes using calorimetry, constant pressure for I, constant volume for I.
We saw how Hess's law lets us calculate enthalpy changes indirectly because the path doesn't matter.
And how standard enthalpies of formation provide a universal reference point for calculating ADISH for almost any reaction using that handy products minus reactants formula.
Finally, we tied it all back to our real-world energy sources, fossil fuels, and the connection between the combustion CO2 levels and the greenhouse effect and climate change.
It shows how these core chemical ideas are absolutely essential for understanding the energy challenges and environmental impacts we face today.
It really does. So thinking about all this, with this deeper grasp of thermochemistry, what responsibilities do we have, as informed people in shaping our energy future? How can this chemical knowledge help drive the new solutions we clearly need?
That's the big question, isn't it? Food for thought.
Thank you for joining us on this deep dive into thermochemistry. This has been a last-minute lecture production.